Time to look at another exam, and it's differential equations. This is the second exam from spring 2024, so we're talking about systems, matrices. That's right, we're going into the matrix. It's going to be a fun exam, and I hope you're ready to do some work. And as always, if we want the credit, we write our names on it. And so first things, we'll put our name, and then we'll be ready to go. Full name, of course, right? So we get full credit. All right, let's begin. Number 1. So we have 2 large tanks with brine solution. And brine is another name for salt water. I might say brine, I might say water. For this problem, they mean the same thing. And they're set up as illustrated in the following diagram. So let's see what's going on. So we have tank 1, and we see that from the outside we have an inflow. And it's a little bit salty there, right? 2 gallons per minute, 5 ounces per gallon. Between tank 1 and tank 2, we actually have flows both ways. So we see 5 gallons per minute going from 1 to 2, and 8 gallons per minute going from 2 to 1. Now at tank 2, there's one other thing, which is we have an outflow of 4 gallons per minute. Now quickly noting the in versus the out in our system. We have 2 gallons per minute coming in, but 4 gallons per minute going out. What is that telling you about the amount of brine? It's going down because the in is less than the out. So the water levels in the tanks are changing. And this is probably going to be one of the hardest things about this problem. In fact, I think it will be the hardest thing about this problem. But we'll deal with that in a few minutes. Okay, so let's keep reading. Moreover, we have that initially, which means that time t equals 0. Tank 1 has 15 gallons of brine, 15 ounces of salt. Tank 2 has 24 gallons of brine, 10 ounces of salt. Set up, but don't solve, an ODE system of the form x prime equals a of tx plus f of t with initial conditions x of 0 that models the amount of salt in the 2 tanks for the first few minutes. Now, why is it being really careful with the phrasing here? Well, remember how we said the water levels are dropping? Well, eventually that means things are going to empty out, and that means that the system has to do something different at that point. It's saying, don't worry about that. Just say what's happening for the first few minutes until something empties out. So that's why that's there. That's actually what this parenthetical comment is. All right, good. Well, let's start by thinking about the water levels. Okay, so I think this will be helpful. Now we know initial water levels, right? So tank 1 has 15 at the start. So initially it has 15. Okay, but it's not going to stay at 15. What's going to happen? Well, let's look at our inflow versus our outflow. We have 2 plus 8 coming in. We have 5 going out. So if we think about that, we have positive 10, negative 5 as our net 5. So that says, the water levels are rising. So we can write this as 15 plus 5t. So that's the water level in tank 1. Okay. Now, what about tank 2? Well, okay, let's talk about tank 2. What do we have? Well, initially it has 24 gallons. Okay, so it's 24. Now, let's look at the inflow. Well, we have 5. What about the outflow? 8 and 4. So we have 5 coming in and then a net 12 going out. So if we 5 minus 12, okay, that's going to be negative 7t. So that's our water level in tank 2. All right. So in other words, after t minutes, there's 24 minus 7t gallons of solution. So you'll notice here the negative. So that actually says tank 2 is going to empty out. It takes about 3.5 minutes. Okay, good. Now, that's important, and we're going to need this as we go about setting it up. Okay, so what are we doing? Well, we have our form. We wanted x prime equals a of tx plus f of t. Now, notice here, you see how you have these bold x's and this a is capitalized? This means vectors and a matrix. So we're not writing it as two separate equations, we're writing it into one matrix form. So we're going to think of our vector x as having two pieces. We can call it x1, x2. And what is x1? Well, x1, that's the amount of salt in tank 1. And I'm not writing the of t as I should, but all of these are changing with time. x2, that's the amount of salt in tank 2. All right, and great. So what are we after? Well, we want to figure out what's going on. And we know how to figure things out because our underlying philosophy when it comes to working with tank problems is we do the following. It's always in, subtract, out. Right? This is the whole thing. If you have a tank problem, you just have to remember, take your in, subtract your out. Life is good. All right, so let's work on that. Okay, so we'll start with x1 prime. How is the salt in the first tank changing? Well, we'll start with the in. We do have an inflow. So we have 2 times 5, 10. So 10 ounces of salt per minute coming from the outside. Anything else? Well, yeah, we have this 8 gallons per minute. Now that's a flow rate. We also need to times by a concentration. Remember here we took 2 times 5? The 2 was a flow rate. The 5 was a concentration. So 8 is a flow rate. Okay, what's the concentration? Well, to find the concentration, we need to say, well, how much salt is there in tank 2 versus how much liquid is there in tank 2? Well, we know how much salt there is in tank 2. That's x2. And we actually know how much liquid there is in tank 2. That's this expression. 24 minus 7t. All right, that's the only two ways that something comes in. How about out? Well, there's only one way. So we're going to subtract, and now what do we have? Well, we have a flow rate of 5, and what's our concentration? It's x1 over, that's the amount of salt, over the total amount of liquid, 15 plus 5t. Now we can rewrite this as, we'll put the x1 first, and we can say, okay, 5, that's 15 plus 5t, everything has a 5 in it. So the thing that says minus 1 over 3 plus t x1. Now here, unfortunately the 7, nothing really simplifies, so we'll write it as plus 8 over 24 minus 7t x2, and don't forget plus 10. All right, so there's our change for x1. x2. Okay, similar process, x2 prime. Okay, in. Well, there's only one in. It's right here. And how does that work? Well, our rate is 5. Our concentration, x1, over 15 plus 5t. And that's it. That's the only in. What about out? Well, we have two sources of outflow. They're 8 and the 4. So combined, our flow rate out is 12. Our concentration, x2 over 24 minus 7t. And that's it. Okay, so again, we'll write this. Similar, we'll put the x1 first, and we have the 5s as we have before. So it's 1 over 3 plus t x1 minus 12 over 24 minus 7t x2, and then there's nothing else. I'm going to write this as plus 0, because it's always true. You can always add 0 to the end of something, and you haven't changed it. Now we're ready. We say, okay, we can think of this part over here. This is acting as our x prime. And then this part here, what's this? This is our f of t. And that part here, this is going to be our a of tx. So we just now have to sort of push everything in the right way. So let's see what's going on. So we can say, all right, x prime equals, and now we're going to have a matrix x plus 10, 0. And the key is these coefficients. And you'll see that's why we wrote things in very particular orders. x1, then x2, x1, then x2. So it's minus 1 over 3 plus t, 8 over 24 minus 7t, 1 over 3 plus t, and minus 12 over 24 minus 7t. All right, that's our system. X prime equals a of tx plus f of t. Cool. Nice. Ah, wonderful, wonderful. So we can throw a box around this and celebrate. Well, hold on. Let's make sure we answered the question, right? So we've written it in this form. We've set it up. We don't have to solve it. Oh, thank goodness. Oh, right. There's this other piece, initial conditions. Okay, so there's one more thing we have to write. What is x at time 0? Well, the answer is how much salt is there at time 0 in tank 1 and tank 2. And that's up here. So we see that tank 1 initially has 15 ounces of salt. So that means 15 in the first slot. Tank 2, 10 ounces of salt. So 10 in the second. And now we are done. That's it. Whew! Wow, what a problem. But of course, the key thing is to remember, hey, things can vary. And so when you see this a of t, that just means, oh, water levels might be changing with time. So that's why you might get functions of t. But the two key things are, make sure you understand the water levels, brine levels, if you will, and remember in minus out. And if you do that, you're in pretty good shape. Life is good. All right, well, let's keep moving on. Number 2, consider the following system of differential equations. X double prime plus x minus 2y is t squared. Y double prime minus x is e to the t. Using the method of elimination, so we're very explicit here. We want to use the method of elimination. Obtain a single differential equation for x. In other words, there's no y terms involved. Do not solve the resulting equation. Oh, whew, good. Another one that we don't have to solve. Don't worry, I'm sure at some point we will get to solve a differential equation. I know you're like, I want to solve a differential equation. That's why I'm in the class. But we'll get there. We'll get there. Okay, so what is it talking about? Well, so method of elimination, we're going to use our D notation, and we're going to be doing some Cramer's rule type arguments. So let's first start by rewriting this. Now there's one thing, I don't know if you noticed it. I hope you saw it. In the first equation, I'm going to write down as is, no worries. But did you see the second equation? It wrote as y double prime minus x. We usually like to put the x's before the y's. And just convention, you just want to have them in the same order in the two equations. So I'm going to write this as minus x plus y double prime. All right. Now, we rewrite things with our D notation. Now, how does that work? Well, remember, what does D stand for? It stands for derivative. So every time you see a derivative, there's a D. So if you see two derivatives, two D's. So this x double prime is going to become a d squared. And then we see a plus 1. So d squared plus 1x. And here there's nothing to do. All right, great. Now here, again, we can think of this as minus 1 times x. And, well, we have our d squared y, because it's second derivative. And we get e to the t. All right. As matrix notation, this is d squared plus 1 minus 2 minus 1 d squared, and xy equals t squared e to the t. All right, so I'm putting it to matrix form so we can use our matrix techniques. And in particular, we're going to be using the technique of elimination that corresponds with Cramer's rule. Now, it's important to remember which variable are we after. Are we after x or after y? And so, well, it tells us we're after x. Okay, so we're after our x variable, and it's important to remember which is the x column, the coefficients for x, because that will play a role. Now, we're ready. Here's the idea. We're going to take this matrix here and take the determinant of it. So d squared plus 1 minus 2 minus 1 d squared and x equals, then on this other side, we're going to replace this column with these functions. So t squared e to the t minus 2 d squared. And most of the work, we're over halfway done now. We just have to finish taking these determinants, and we'll be in good shape. All right, so here we go. What do we have? Well, we have here d squared plus 1 times d squared. Subtract minus 1 times minus 2, x. Over here, we'll have d squared t squared. Subtract minus 2 e to the t. Now, this becomes d to the fourth plus d squared. And then we have minus, 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 triple minus. So that's a net negative 2x. And all right, we'll rewrite this again. Minus, minus makes plus. All right, now just remember, d to the fourth times x. What does that mean? Well, it means 4 derivatives of x. So you can write that as x. You could use x prime, 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 prime. Or usually once I hit 4, I start using that notation. So the fourth derivative of x plus 2 derivatives of x minus 2x d squared t squared. 2 derivatives. So start with t squared, 1 derivative, 2t. Okay, now take another derivative. Derivative of 2t, 2. So that's 2, and then plus 2e to the t. All right, great. But now what do we do? Well, this step is important. It is circle your answer. In this case, put a box around it, because we're done. Because what have we done? We have a differential equation, 1. It's for x. There's no y's. That's what it wanted. Life is good. Nice. All right. Well, let's keep going. Number 3. Consider the following system. So we have t squared times x prime is equal to 0, 2t squared, 1, 1, x. All right. Now it looks like a nice matrix, but see how we have entries that involve t? Ugh. So we can't use our techniques of eigenvalues, eigenvectors. We really don't have good techniques right now to solve this, but that's okay. Maybe we won't have to. Let's see what we do need to do. So part A, verify that this is a solution. Verify. Now the nice thing about verify is it's basically free points, right? Because what do? Verify means what? It means plug in. And so when you see verify, we're like, aha, we're going to plug in. And what do? Well, we just have to say we plug it into both sides, and we're going to compare our answers. And we know if it's a solution, they have to match. Okay, so let's go through and see what happens. So we'll start with the left-hand side. So the left-hand side, what do we have? Well, we have t squared x prime. So that's t squared times. Now let's go through this carefully. We're going to take the derivative of each term, because when you're taking the derivative of a vector or a matrix, term by term. T is showing up in two places, so we'll do product rule. So let's see, we have the derivative of the first, so the derivative of 2t squared would make 4t times the second. Then the first, which is 2t squared, times the derivative of the second. Now, the derivative of e to the minus 1 over t, well, it starts e to the minus 1 over t, right? Excuse me. So it starts as e to the minus 1 over t, right? Well, and then what? Chain rule. So what's the derivative of minus 1 over t? All right, so derivative of minus 1 over t, that's minus t to the minus 1. So if we take a derivative, the minus 1 comes down. So that'll be a minus 1 t to the minus 2. So the two minuses cancel, and you get 1 over t squared. Okay, so times derivative of derivative of minus 1 over t squared. Okay. Downstairs, derivative of the first is 2 e to the minus 1 over t, and then plus the first 2t plus 1 times, again, the derivative of e to the minus 1 over t, which is e to the minus 1 over t times 1 over t squared. Okay, let's multiply the t squareds in. What do we end up with? Well, here we'll have 4t cubed, because t squared times 4t. And then here, the t squareds cancel. Now there's another t squared, and so that will give us a plus 2t squared e to the minus 1 over t. Here we have 2t squared e to the minus 1 over t. And then the t squareds here cancel, so we can say, oh, plus 2t plus 1 e to the minus 1 over t. All right, so there's the left-hand side. All right, now we've got to do something similar. We've got to do the right-hand side. So we begin. The right-hand side, what happens? Well, we're going to take 0, 2t squared, 1, x. Okay, that's 0, 2t squared, 1 times 2t squared e to the minus 1 over t, and then 2t plus 1 e to the minus 1 over t. Okay, matrix multiplication. So we're going to take 0 times that and 2t squared times that. Well, notice we can multiply the 2t squares together, and what do we end up with? Well, 2t squared times 2t makes it 4t cubed, and 2t squared times 1 is plus 2t squared e to the minus 1 over t. Good. Now here we're going to 2t squared e to the minus 1 over t plus 2t plus 1 e to the minus 1 over t. So we're going to, 1, right? So we can actually just add the coefficients of e to the minus 1 over t. 2t squared plus 2t plus 1 e to the minus 1 over t. All right, that's the right-hand side. And now our great and the great is, do they match? Well, let's check. Well, if you factor out e to the minus 1 over t, you'd have 4t cubed plus 2t squared. And again, factor out e to the minus 1 over t, you'd have 2t squared plus 2t plus 1. And so we say, aha, these match. And so that means it's a solution. And we're done. Because in verifying, you just plug in and make sure things match up. All right, good. We found a solution. Well, there should be a second solution. There's also a second part. find a, b, c, d, so that x2, which is at squared plus bt plus 1, and ct plus d is a solution to the system. Notice there's no e to the minus 1 over t's. Okay, so how do you find a solution? Given that we know roughly what it looks like, what can we do? Well, any idea? Yeah, let's do the following. We're going to plug it in. Why? Because we know it's the solution to the system. So it has to satisfy it. So it's actually just like part A. So plugging in, it can be useful for verifying, but it also can be useful in finding solutions. Particularly if you say, I think my solution looks like this. Then you say, okay, plug it in and see does it work. And or what do you have to do? How do you have to sort of tweak it to make it work? So we're going to plug into both sides. Okay, so here we go. We're going to have our t squared, whoops, not t sub 2, t squared, there we go, x prime. So that's t squared. Take the derivative. Okay, so that's term by term, 2at plus b and c. So that's what? That's 2at cubed plus bt squared and ct squared. There we go. So that's the left-hand side. Now we're going to do the same thing but with the right-hand side. Okay, so we're going to take our 0, 2t squared, 1, x. All right, that's 0, 2t squared, 1, times at squared plus bt plus 1, ct plus d. Okay, so multiplication, you get 0 plus 2t squared times ct plus d. So that would be 2ct cubed plus 2dt squared. And then you're going to get 1 times the first plus 1 times the second. In other words, we're just adding these together. So you say, okay, adding them together, we'd get the a t squared. The t's, you give us b plus c t. And then the constants are d plus 1. Now, what do we know? We know it's a solution. Given that we know it's a solution, what must be true? Well, what must be true is that when we plug into the left-hand side, we get what we plug into the right-hand side. In other words, these parts have to match. Okay, so we know that these parts match, which means they have to match in their entries. So the first entries have to match. The second entries have to match, which means that the coefficients have to match. So now we're just going to say what's true about our coefficients. What do we need? Well, we compare the coefficient for t cubed. We say, okay, we need that 2 times a equals 2 times c. Come over here and we say, we see that b has to equal 2 times d. All right, what else? Here we see c times t squared has to equal a times t squared. So we have that a equals c. You say, oh, wait a second, we already have that. That's true. You see, we already have a equals c. So, okay, we already knew that one. Then we say, well, wait a second here, there's no t. Well, there kind of is. It's 0 times t. So we say, oh, b plus c has to equal 0. And there's no constant. Well, again, kind of is. It means that d plus 1 has to equal 0. All right, well, now we start saying, can we solve any of these? And make sure my d looks like a d. There's one that we can solve really quickly. We say, oh, d, that has to equal -1. All right, and we say, oh, wait a second, look at the b. That b is 2 times d. So that tells us that b has to be -2. But wait a second, b plus c equals 0. We now know that b is -2. So -2 plus 2 equals 0. So c has to equal 2. Hey, but a equals c. That tells us that a also has to equal 2. And that's our answer. So we found A, B, C, D. Now the solution, we don't need to write this down, but if we did, it would be 2t squared minus 2t plus 1, and then it'd be downstairs 2t minus 1. So that's x2. But again, we're after A, B, C, D, so that's what we're looking for, A, B, C, D. All right, well, that's not so bad. So that's kind of fun. And so yeah, I guess the mantra for this one was plug it in, right? Plug it in. It's a really useful tool. And even though we learned it way back when, in fact, I think we learned it on maybe like day 1 or day 2 of the class, but it's still really good. It's an amazingly great technique for using to solve differential equations. Number 4, find the general form for solutions of the system dx dt equals 10 minus 550x. All right, so dx dt, by the way, has another name. We also call this x prime. And so, all right, well, great. Now we're getting into the fun stuff where we have a 2 by 2, and they're numbers, no functions. So we get into our eigenvalues, eigenvectors. And in fact, whenever we see a 2 by 2 matrix, we go and say, hey, let's talk about our eigenvalues. What's going on? So our first reaction is always eigenvalues. Okay, so here we go. We're finding our eigenvalues. So we're going to take 10 minus lambda minus 5, 5 minus lambda. So, right, so this is our a minus lambda I. So we're subtracting lambda off the diagonal terms. All right, so this will become 10 minus lambda times minus lambda, subtract 5 times negative 5. Okay, or that is lambda squared minus 10 lambda, and then minus 5 times minus 5 is a plus 25, which is also known as lambda minus 5 squared, which tells us what? It tells us our eigenvalues are 5 and 5. In other words, repeated. All right, great. So actually, repeated eigenvalues aren't bad. There's wonderful things we can do. Now, I'm going to do it using our matrix exponential rules. And at least let's do it. Maybe we'll do it twice. Let me show you the way I would want to do it, because I tend to be, let's make this easy on ourselves, because we should love ourselves, right? Yes, 100% we should love ourselves. We should take care of ourselves. And so we say, okay, great. So what do we do? Well, now that we know the eigenvalues, we can say, hey, that means that e to the at, we have a formula for this. That's e to the lambda t times the identity plus t a minus lambda I. Well, we know these things. So e to the lambda t becomes e to the 5t. The identity is this 1, 0, 0, 1. That's what that means. Plus t. Now a minus lambda I. So this is a minus lambda I. So we're putting it in 5. So you have 5 minus 5, 5 minus 5. Well, all right, that's e to the 5t, and I'm going to squish it into a single matrix. 1 plus 5t minus 5t, 5t, 1 minus 5t. Now, not the answer, but the thing to remember is that e to the at is a fundamental matrix. What are fundamental matrices? Well, they're a way of sort of cramming solutions in together. And so each column is a solution. So we say, ah, great. So now, using the columns, we have the solutions. So for the general form, we combine the columns together in superposition. So our answer would be, all right, take some constant, c, times the first column, don't forget the e to the 5t, so e to the 5t, 1 plus 5t, 5t, plus some constant d times our second column. minus 5t, 1 minus 5t. And that is the general form. So general form says, what do all solutions look like? And so you have to have some constants in there. So constant times first column plus constant times second column, and we're done. Whew. All right. Now that's if you want to use matrix exponentials. But what if you're like, I'm not feeling matrix exponentials today? Can you do it another way? Absolutely. So let's do it without matrix exponentials. When we see repeated eigenvalues, what comes into our mind is, generalized eigenvectors, what really means we're going to come up short. Okay, so we're going to start by writing our a minus lambda I. So we have our a minus lambda I, and we put in, of course, our lambda is 5. 5 minus 5, 5 minus 5 times something, and we want to get 0, 0. Okay, do we know something that works? Well, yeah. 1, 1. We can spot that. Now this is our eigenvector, v. Okay, so we're going to write that. Now, once we have that, next part we say is, okay, similar thing. A minus lambda I, 5 minus 5, 5 minus 5 times something equals 1, 1. So this part right here is our v. I'm just copying it. Say, okay, is there something that does that? Well, yeah. I mean, essentially, you can think of what's happening here is that the entries are combinations of the columns. And you say, well, this first column looks a lot like that, except there's a factor of 5. So you say, okay, so I can make it 1/5 0. Now, there's lots of things you could do, but this is one that's fairly simple. And we'll call this w. And now, once you have v and w, you say, well, I know the rules. So what the rules say is that our first solution looks like e to the lambda t times v, or that's e to the 5t 1, 1. Our second solution looks like e lambda t times v, so it's sort of like, aha, you bump. But then there's sort of like, well, you got to do a little bit of a fudging factor. So that's e to the 5t, and then it's t 1, 1 plus w. All right, that's 1/5 0. So those are our two solutions. And now for superposition, and you get your general form. So our final answer would look like x equals some constant c, e to the 5t 1, 1, plus some constant d, e to the 5t, and you can leave it like this, or you can smush it together. I'll smush it together. So you get t plus 1/5 and t. And there you go. All right, good, good. Now, as you look at this, you might say, these don't look the same. That's okay. And there are many ways to write general form. And it turns out that if you do it right, you can get different ways, and that's all right. There's different correct answers. The key thing is that any solution that can be written like this for a choice of C and D, there's some other choice of C and D that gives you the exact same thing. And so we're good, life is good, life is wonderful. All right, well, let's keep going. Number 5. We're asked to solve for x of t and y of t given x prime is 2x minus 9y, y prime equals x plus 2y, and there are some initial conditions, x of 0 equals 0, and y of 0 equals 1. So we're after a particular solution. Now, I like to put things into matrix form so we can use matrix tools. Those matrix tools aren't bad once you get the hang of them. Since we already have x and y, to help limit my confusion, I am going to write this as z. So I'm thinking of z here. This is a vector where x on top, y on the bottom. And so you get z prime, that's the derivative on the left-hand side, equals something z. And here we're going to put our coefficients. So we have 2 minus 9, 1 2. And, you know, we double check, make sure they're in the right order. They have in the past sort of like been sneaky and switched things, but we're not going to let them catch us off guard. X first, Y second, good. Okay, so now we have a 2 by 2 matrix, which means step 1, find eigenvalues. All right, so here we go, eigenvalues. And so we're going to take our determinant of 2 minus lambda minus 9, 1, 2 minus lambda. So that's going to be 2 minus lambda squared, subtract 1 times negative 9, or if you like, this is the same as lambda squared minus 4 lambda plus 4 plus 9. So I guess we could have written this as plus 13. Now, there's a couple ways. You could have done some set n equal to 0 and solve, but I'm going to do this like if I'm not clever, so I'm going to assume we're not doing anything wild. We get down to this, lambda squared minus 4 lambda plus 13. We say, does it factor? Could it factor? No, it doesn't factor. So we say, okay, what can we do? Well, what we can do is you can say, all right, quadratic formula of that. So, okay, so we have lambda is equal to 4 plus or minus the square root of, negative b, that's where the 4 is coming from, b squared, 16, minus 4 times 1 times 13. So 16 minus 52, all over 2. Now, 16 subtract 52, that's also known as a negative 36. The square root of a negative. Things are about to get a little bit complex. Okay, so we're almost there. 4 over 2 gives us 2. Then square root of 36 is 6. Then there's an I, because then the negative. 6i over 2 makes this 3i. So here are our eigenvalues. Now, by the way, what's another way you could have done this? I'll go ahead and point out what you could have done. You could have said, if you look at this, this is lambda minus 2 squared. It's the same thing. And plus 9 equals 0. Or lambda minus 2 squared equals negative 9. So lambda minus 2, take the square root of both sides, get a plus minus, and because there's a negative, you introduce an I, so lambda equals 2 plus minus 3i. So that's another thing you could have done to go into your eigenvalues. Now, what do we see? This is complex. Okay, cool. Complex eigenvalues. So what are we going to do? Well, I'm going to use matrix exponentials because it's a great tool. But we'll do it twice, right? With matrix exponentials, without matrix exponentials. So we're thinking of this part here as our a. And so we're going to find e to the a t. Well, that is e to the alpha t cosine beta t times the identity plus 1 over beta e alpha t sine beta t times a minus alpha I. All right, so that's our formula. What do we know? We know our complex roots, and this is alpha plus minus beta I. So alpha is 2, beta is 3. So we have e to the 2t cosine 3t times our identity, 1001. Beta is 3, so 1/3 e to the 2t sine 3t. Now a minus alpha I. So we're not a minus lambda, it's a minus alpha. So we're subtracting 2. Now notice the diagonal already has 2, so we're subtracting 2's. So this becomes 0 minus 9, 1, 0. Smush it together. And in fact, smushing is very easy. So this will be e to the 2t cosine 3t. That's the upper left entry, and that's the only entry there. Upper right, you get 0, and 1/3 times minus 9 is minus 3. E to the 2t sine 3t. Okay, lower left, 0. 1/3 e to the 2t sine 3t. And lower right, e to the 2t cosine 3t and 0. Okay, so here's e to the at. Not our answer, but we're almost done. Okay, so how do we get our answer? Well, the thing is, we say, oh, once we have our matrix exponential and we know our initial values, because we say, oh, this really is an initial value problem where z of 0 is 0, 1. So our answer, we need to take e to the at times r 0, 1. Okay, so we're going to write this all again. There's a lot of writing on these tests. And of course, you just have to be patient. And while you're doing this, make sure you copy things carefully, because the biggest challenge is oftentimes just making sure you got it written down right. 0, 1. All right. Now, matrix multiplication. 0 times 1. Okay, so we get minus 3 e to the 2t sine 3t. And then 0 and 1. Okay, so 0 times that, 1 times that. E to the 2t cosine 3t. All right, now is this our answer? Kind of. Kind of. This is the correct z. But we didn't start with z. We started here. See how it's separated out? So we don't want a vector as our answer because it wasn't given to us in vector form. So now we're going to take it and pull it apart and say, well, look, the first entry, the top entry, that's x. The second entry, that's y. So we say our real answer is that x is minus 3 e to the 2t sine 3t. And then y is our second entry, e to the 2t cosine 3t. And that is our answer. And notice we're after a particular solution, and so we're not going to have any constants here. There's no plus c plus d, none of that. We're after a solution which satisfies what we need. Now, this is if you like using matrix exponentials. And I said we'll do it twice. Okay, so let's do it twice. We'll need another piece of paper. Good news, I have paper. And so let's suppose we got down to our complex roots. What do we do from here? Well, now we're going to go after an eigenvector. So you say, okay, so we have lambda, that's 2 plus 3i. So we're going to take a minus lambda I. And we say, okay, well, that would be 2 subtract 2 plus 3i, which is minus 3i, minus 9, and then down here 1, and then 2 minus 2 plus 3i is again minus 3i, times something equals 0, 0. Okay, so this is what we do when we're after an eigenvector. So what goes here? Well, the easy thing to do is pick a row. This row looks simpler. And you fill it in backwards. So minus 3i1, and then you change a sign. Boom, sign change. So 3i1, that's our eigenvector. All right, so now with that in place, here we go. So we have our eigenvector. Now we're going to get our solutions. So we start with our e to the 2t cosine 3t plus I e to the 2t sine 3t. And this part right here is e to the lambda t, just pulled out where you separate the real and the imaginary. We're going to times that by our vector 0, 1 plus I, 3, 0. Where again, this is our eigenvector, we've just pulled it apart, real and imaginary. And we're going to carry out our multiplication. Okay, so to get real, we take real times real. So we get e to the 2t cosine 3t, 0, 1. And imaginary times imaginary. So I squared is a minus. Minus e to the 2t sine 3t, 3, 0. Okay, so this is our first solution. We're going to add the imaginary part. Okay, so here we'll have e to the 2t cosine 3t, 3, 0, plus e to the 2t sine 3t, 0, 1. All right, and the imaginary part is second solution. So now we have two solutions. Okay, good. So with two solutions, we can say, hey, what's our general form look like? So our general form looks like some constant times, and I'm going to smush these together. You'll get minus 3 e to the 2t sine 3t. Then downstairs you'll get e to the 2t cosine 3t plus some other constant. And here, upstairs we'll get 3 e to the 2t cosine 3t. And downstairs we'll get e to the 2t sine 3t. All right, but we need to solve for c and d. We solve for it using our initial conditions. So, z of 0 is, well, c times, here we get 0, and here we get 1. 0, 1, plus d, and then here we'll get 3 times 1, so that's 3, and we'll get 0. Which, if you put this together, that's 3 times d, and there's c, and that needs to equal 0, 1. All right, well, what does that tell us? Well, it tells us d is 0 and c is 1. Now we say, beautiful, so our answer looks like 1 times and 0 times, right? So it's just this vector. That's the answer. Well, it's not really the answer, because what do we need to do? Well, we have to remember, hey, we need now to separate, because that's z. So we separate like we did before. We say, all right, the first slot is our x, the second slot is our y. So this tells us that our solution looks like minus 3 e to the 2t sine 3t, and y is e to the 2t cosine 3t. And there we go. Now, did we get the same answer? You should. It's an initial value problem. If you have an initial value problem, you should always get the same answer. And you'll see minus 3 e to the 2t sine 3t and e to the 2t cosine 3t. All right. Good news is you don't have to do it twice. You only have to do it once, and use whichever method you like. I will say I'm biased towards matrix exponentials because it does make things nice. You got a little lucky here because the diagonal terms just happen to line up and give you just what you needed, because otherwise this would have gotten complicated, even more complicated than it already is. But the important thing is not to do it, Steve's way. Is to do it a way that you'll get correct, because that's what's important. Get the points, all the points. This brings us to our final problem, number 6. Woo! Okay, so we need to compute e to the at. So I think we're going to use matrix exponentials on this one because the whole problem is about a matrix exponential. And we're told our matrix A is 6 minus 7, 1 minus 2. Okay, first step, we need to find our eigenvalues. So I say, okay, no worries. So we're going to do that. We're going to take 6 minus lambda minus 7, 1 minus 2 minus lambda. Okay, so that's 6 minus lambda times minus 2 minus lambda, right? Multiply down the diagonal, subtract, other way, 1 times negative 7. All right, well, that's lambda squared. Cool. Then you get minus 6 lambda and plus 2 lambda. So that'll make minus 4 lambda. Then you get minus 12 and plus 7. That makes minus 12 plus 7 is minus 5. Okay, does that factor? I think it does. It looks like it might be lambda minus 5, lambda plus 1. Let's see, does that make sense? Because you need two things that multiply to negative 5 but add to negative 4. Lambda squared, that's true. Lambda minus 5 lambda is minus 4 lambda. And yeah, it works. All right, sorry. We need to set that equal to 0. And now we see, aha, lambda is 5 and negative 1. Okay, so those are our two eigenvalues. Now, what do we notice? Distinct. We're in the distinct eigenvalue case, and we say, okay, so how do we find e to the at? Well, the distinct eigenvalue case, well, actually, the general thing for e to the at is you have this phi of t, then you have phi 0 inverse, where phi of t is, fundamental matrix. And you might say, well wait, there's no differential equation here. And so you say, well, even if you don't, you pretend like there's this x prime equals ax, what do you do? So you say, oh, well, you find eigenvalues and you find eigenvectors, and then you multiply e lambda tv, and then you've got solutions. Yeah, so that's exactly what we're going to be doing. All right, so let's go ahead and keep going in this direction. So we've got eigenvalues, eigenvectors are next. Okay, so we'll start with lambda equals 5. So we're going to put in lambda is 5, and what do we get? Well, we get 1 minus 7, 1 minus 7. Oh, okay. And times something, we want to get 0, 0. All right, well, what does that? And, well, the answer, 7, 1, right? Just put it in backwards and flip a sign. Say, okay, great. That's our eigenvector. And so we say, okay, so we have a solution would look like e to the lambda t times our eigenvector. Okay, well, what about minus 1? Well, for minus 1, what happens? 6 minus minus 1, 7. Minus 7, 1. Minus 2 minus minus 1 is minus 1. Times something gives 0, 0. Okay, is there a vector that does that? Yeah, 1, 1. We like that vector. It shows up a lot. Okay, so x2, that's e to the minus t, and then times eigenvector. Okay, so now we say, hey, we've got these two, we push them in together, and we make our fundamental matrix. And all right, so I'm going to switch colors here as we go. So now we have phi, looks like, and we'll have 7 e to the 5t, e to the 5t. So I'm pushing that e to the 5t in. And then x2 is our second column, e to the minus t, e to the minus t. This is not e to the at, but we're close. We've gotten this piece of it. So now we got to work over here, this phi 0 inverse. All right, so time for some work on the side. what is phi of 0? Well, if you plug it in, e to the 0 is 1, so you get 7, 1, 1, 1. Okay, that's no problem. Phi 0 inverse, well, 1 over the determinant, which is 7 subtract 1. Don't forget this, you really need it. And then flip the diagonal entries. Change the signs in the off diagonals. Or you can write this as 1, 6, 1, minus 1, minus 1, 7. All right, so now we multiply these two pieces together, and then life will be good, because we'll have the answer. All right, so we're ready to do our last hurrah. So e to the at. We know that's phi of t times phi 0 inverse. So we copy the pieces down. 7 e to the 5t, e to the minus t, e to the 5t, e to the minus t, times we have 1, 6, 1 minus 1, minus 1, 7. And the 1, 6 we can leave outside. That's a scalar. But we really need to do the matrix multiplication. So 1, 6 times, and here we go. We're going to practice matrix multiplication. So 7 e to the 5t, subtract e to the minus t, minus 7 e to the 5t, plus 7 e to the minus t. Now e to the 5t, subtract e to the minus t. And finally, minus e to the 5t plus 7e to the minus t. And we're done. We did it. We made it all the way through. Woohoo! Good on us. Good on us. All right, well, I hope if you took this test, you did well. And if you're studying for another test, I hope you're going to do well. And thank you for being here, and I hope to see you again. Bye.